Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you, Anna. Hello, everyone. Good morning, good afternoon, good evening from me as well. I am Guilherme Martinez-Roura from the International Telecommunication Union, and I would like to welcome you all for joining today's AI for Good event on AI-powered wearable robots providing personalized assistance for mobility and biomechanics, organized by the ITU. Today's session will delve into how advanced wearable exosuits restore mobility in older adults by adapting to the user intent and biomechanics, exploring AI-driven control, real-world generalization, and new open-source datasets. This session is part of the AI and Robotics Discovery Series, which features expert talks on the state-of-the-art developments in autonomous robotic systems to advance the United Nations Sustainable Development Goals. We have a very distinguished speaker today, but as always, we're counting on you, the participants, the audience, to help create a very interactive session. As a reminder, the audience can leave questions in the AI for Good neural network chat room that will be answered during the Q&A section. So without further ado, I would like to introduce our speaker today. His name is Professor Aaron Young, and he is Associate Professor and Woodruff Faculty Fellow in the Woodruff School of Mechanical Engineering at Georgia Tech. Aaron, welcome, and the floor is all yours.
All right. Thank you so much for having me today, and thanks for the AI for Good for inviting me to this talk. Let me my screen share. Okay, so hopefully it can be seen now. Yes?
Yeah.
Okay, great. So thanks again for having me today. I'm Aaron Young. I run the Exoskeleton Prosthetic Intelligent Controls Lab at Georgia Tech, and our mission is to improve the human condition and specifically through the application of robotic systems. We have many different areas that we do this at Georgia Tech, primarily through the Institute for Robotics and Intelligent Machines, where many different faculties and lab groups work together to solve some of these big health problems. And I'll start with just kind of an intro of wearable robots. Here are just tons of different projects that we have here at Georgia Tech and different robots that we use on a daily basis, where we look at how can we assist different individuals, primarily with mobility disorders. So these are older adults, individuals with stroke, pediatrics, neural rehabilitation, like for cerebral palsy or traumatic brain injury. And then we also go outside just the clinical realm into thinking about robots for industry workers and using them to assist in heavy manual material handling and trying to reduce injuries in these in these groups. And so these are a range of different devices. We have devices that target the lower legs, that target the back, that target arms, and the goal is really to broadly improve human health and mobility, both in clinical situations and in industrial settings. So this gives a little bit, and the idea of these wearable robots is to provide direct assistance to these parts of the body. So let's talk a little bit about the clinical significance. The older adult population in the United States is growing rapidly, and difficulties with mobility is the largest source of disability across the age groups, but especially in older adults. So this is one of the biggest areas that we want to see improvement on. This leads to much increased costs, and much poorer quality of life. Fear of falling and incidents of falls lead to major secondary problems after falls, and degrade quality of life. So we want to prevent falls and improve mobility capability in homes, in communities, and out in the real world. So this is really the kind of the main goal that we hope wearable robots can eventually really help with in our society. There's a lot of new cool technology out on the market that is robotic in nature, that is meant to restore, augment human locomotion performance. I'm just showing a small subset of those. These are 3 of the FDA-approved exoskeletons. But what you can see right now is a lot of the things out there are large, bulky, often require mobility aids to use, and is still, relatively not used in homes, in communities, and environments. And this is something that we hope to change over time. And so it's exciting. There are companies that are really working on this technology, and we are working on partnering with many of them to really improve the technology such that this could be something that gets out of the clinic and into patients' hands. Let's get into a little bit more of the technical details. So this is kind of the main measure. So this idea of energy cost has really been the gold standard, and I think it's important for us to establish kind of a what is good. What does good assistance mean for patients and for people using these devices? Energy cost has kind of been the predominant measure. And I'm showing a chart. This chart is somewhat dated, of a review paper that Dr. Greg Sawicki and I put together back in 2020. The number of these are all the devices that we would say have been published that significantly broke what we call the metabolic cost barrier, which means if you put on a device, it's actually it is improving you beyond not wearing a device at all. It took a long time for the field to cross that point, because when you put on a device, it adds a big metabolic penalty to you. And so not only is it making up for its own weight and inertial effects, but it's giving you additional augmentation. So we would call this full human augmentation. Any of the devices here, these were all the devices leading up to 2020 that had successfully crossed this barrier. Now this list is 3 to 4 times this large. So in the last 10 years, I would say the field has been very successful in creating devices that can reduce energy costs, as in make it much easier for people to walk or climb stairs or go up ramps in very specific tasks. And all of these devices primarily only augment in a single task. And so that really, to me, we have shown that we can build these devices, that we can actually improve human energetic economy and provide significant augmentation, and yet they're still not being used out in the real world very ubiquitously, which is, of course, the real goal that we would like to see. So how do we see these benefits out of the lab? Most of these are done on a treadmill. Most of these tests are done on a treadmill, and these devices are very effective if you're just walking at a single speed on a treadmill. But what has turned out to be extraordinarily challenging, and part of the reason that these devices are not going out in the real world, is the controls problem. So the humans, in fact, are not steady state walkers. They are very fast and very unpredictable in terms of how they move. And being able to create controllers that can handle the very high variability of different tasks that we see out in the real world is very challenging, when a lot of these controllers are kind of handmade to do extraordinarily well on single tasks. Usually that does not extend very far to the wide range of things that people do, even just to get around, in the community, like going to the grocery store. You'll have to go up and down curbs. You have to get in and out of cars. You have to do lots of transitions between tasks. You have to push things, you have to carry things. This is very challenging to create controllers that can handle this wide diversity of tasks that we do in our homes and environments. Even though we can successfully augment in the lab, this is really the key challenge: is how do we create controllers that are relatively, we're going to use the term task agnostic, that can handle the huge variety of tasks that we might face in real world environments. And that is really where I think AI comes in, and really relevant to kind of this talk. We're going to focus on the use of AI in this technology. And I think it's a very promising future. So what we have really been investing in is creating really big data sets in the human-robot interaction field. In order to be able to train these deep learning systems, and people who are familiar with this, deep learning is kind of this subset of AI that really requires massive data sets in order to reason like humans and to perform. Humans are able to handle very high levels of task diversity, even things that they haven't necessarily encountered before, and still not fall over, for example. That's very hard, though, for a robot to do. And we really want to leverage kind of these AI systems to have that kind of reasoning similar to what humans are able to do across huge levels of task variety. So to us, AI is really this key capability to unlocking what we would call task agnostic or task generalizable control, where we could generalize across lots of different tasks. And if we could do this, then it opens up lots of really cool applications. This just goes over a few that we look at. One is in the mobility challenge. So this will probably be the main focus, which is this idea of personalized AI that basically helps you get around the community. So a permanent assistive device. We also use these in robotic prostheses. So AI, where you have an entire limb being replaced, and we want these systems to basically function like bionic legs, where it's fully replacing both not only the mechanical capabilities of the leg, but also the intelligence that our legs have to handle wide varieties of tasks. We also use AI in rehabilitation research. So, for example, where AI agents are retraining people to walk and trying to encourage propagate biomechanics over time. So AI can be very valuable there. And then even outside of just the clinical realm, using them in manual material handling and industrial tasks where injuries, overwork, overuse, fatigue is very common. Being able to adapt AI to these techniques to really improve people's ability to work with robots and maintain their jobs and health is also very critical. Okay, so we'll talk about kind of two competing objectives, which might sound competing, but we really want to train AI systems to handle both of these. The first is this idea of generalization, which I've already talked a bit about, which is really the ability to perform well on novel tasks, but also novel users. So we don't necessarily want to have the AI system get a whole bunch of training data, for example, from a specific user. We want it to be able to generalize to a brand new user and ideally to brand new tasks that has not encountered before. So this is one big challenge in the field. The other is this idea of personalization, which is adapting to specific user needs. So especially in patient populations, you'll see a high amount of heterogeneity in terms of the physical capabilities of these people. And the AI system really does need to adapt to both people who are going to be walking on the very low end of the scale and people who are going to be ambulating, much higher on that scale, and being able to individualize or provide assistance that is suited to that individual's needs is very critical. And so we would ideally like both of these systems to happen without the need of lots of training and sort of subject specific heuristic tuning, which is very common sometimes in this field. All of that we're trying to avoid by training really large scale AI systems. Okay, So let's talk a little bit about control. Control has been really the main bottleneck in being able to get these systems out historically. And this is kind of a block diagram showing, this very high level how exoskeleton control works. Today, most industry devices will use a controller somewhat similar to this one, which is that you have a set of state estimates that basically estimate the world or the environment. So we might specifically identify that someone's trying to walk on level ground or try to go up a ramp or try to go up a stair. And oftentimes there are different control functions formulated, for example, doing stairs or doing sit to stand or doing level ground walking. Those are very biomechanically different tasks and require a different assistance profile in order for the device to be effective. So that's kind of today, this state estimation occurs where different activities basically are grouped as different states. And then through a lot of engineering, usually a specific torque profile is created for each of these different states. So for example, if you're wearing a hip exoskeleton, which is the example that I'm going to use here, you might have a specific profile that the device applies to you while you're walking on level ground, and a different profile for going up a stair, or a different one for doing sit to stand. All those are very different, and the optimal profile is going to vary across tests. So this is kind of the standard for control, but it's historically faced with two major problems. One, identifying all the different things that people do is extraordinarily challenging. In fact, there are certain tasks that are hard to even classify. I just gave the example of different ambulation modes, but in fact, to really have good control, you would need to identify far more than that. You might want to know, for example, how fast they're walking. That's going to change the torques that the device is going to do, or what the grade of the ground is, or if they're doing load carriage, or if they're walking asymmetrically, or if there's an object that they need to step over, or how to identify slips and trips, right? There's many different things that people do, and this requires, almost an intractable number of different states if you want to run a controller with this kind of strategy. So that's one problem. This idea of scale becomes very challenging with what we would call external state identification. And then even if you could do all of that identification with different control logic or with AI systems, you would still have to design a very specific, what we would call mid-level controller, basically this torque trajectory that you see for every possible combination of those states. And these usually are very time intensive. They require a lot of work for companies or labs to put together basically these optimal torque profiles, often through a lot of experimentation. So this makes for a very difficult challenge. So we have taken a very different approach at Georgia Tech to how to handle this problem. And rather than trying to estimate everything in the world, we have turned to, well, the human really knows a lot about what's going on. And rather than trying to replicate the brain fully and do all of the state estimation, we would rather play off the human and understand what's going on internally. And so our AI systems are not trained to recognize the entire world environment, but rather to recognize the internal physiological states of the human. And this has been a huge breakthrough for our AI systems to perform really well and be heavily in sync with how humans are moving, such that they have smooth and enjoyable assistance in all of their tasks. So this has been the strategy. And what we mean by this internal state estimation is that you can estimate, for example, the internal joint moments that the muscles are making at the joint. So basically, you could think of it as our AI system wants to know how much energy you need at a joint. Doesn't necessarily care about what you're doing, but really, if I'm assisting the hip, what is the human physiology trying to do? What joint moment? So you could think of that as like a torque is being exhibited at each of the internal human joints. Okay, and so this basically collapses this control problem to a huge neural network where you have exoskeleton sensor data coming into the neural network, and out of the neural network, you basically have internal estimates of the human joints. In this case, joint moments. We have a little bit of mid-level control, which basically just scales it to how much to the correct assistance and doing some filtering for the device output. So it's very what we would call end-to-end. So it's just taking sensor data and outputting the internal scaled joint moments of the human. So a very different style of control. It doesn't necessarily care about what you're doing, or it doesn't need to know where you're at in the gait cycle or what kind of task you're performing. It just needs to know, what are the requirements, the energetic requirements from a kinetics perspective of what the human is doing, and tries to estimate that end to end. And if we can do that very accurately, then we can create a controller, a closed loop controller that might be more task agnostic. Okay, so how did we do this? So let's talk through a little bit of the details. First, this is kind of what we have from a standard exoskeleton. This is not too different in terms of sensing. No sensing requirements here that are different than devices that are currently commercially available. So there is no neural sensing or anything of that nature. This is all just mechanical sensors embedded in the robotic device itself, so very easily deployable. Typically, this is a combination of encoders on the joints that provide position and velocity, and IMUs that provide accelerations and angular velocities on the segments. In this case, since the hip exo, you have one on the pelvis and one on the thigh. And this goes through what we call is a temporal convolutional neural network. This is a type of RNN that is very good for biological data, time series data, because it has what we would call these exponentially dilating layers. So basically, it convolutes data over time series very efficiently and very well. And this is what we see in kind of lower limb data. There's a lot of information in the time series. You don't want just the data at the current time step. You want to look over about the last second of human activity to get at what the human's doing. These TCNs do this in a very time efficient manner, where we can run these at high clock rates. In this case, we run at 200 hertz. So every 5 milliseconds, it's basically making a new command to the motors about what should be done. And at the end of this network, it's predicting internal hip joint moments. So this is the idea of these exponentially dilating layers over the convolutional neural networks. And then at the end, you have a traditional set of dense layers in the neural network, which can be fine-tuned depending on the application. Okay, and we showed some years ago that these TCNs outperform other standard deep learning approaches like transformers or LSTMs or CNNs, other things that you might be familiar with. This I think many different groups now have shown that this type of neural network works very well for kind of time series biological data like this. Okay, so moving on to kind of the robot side of it, we implemented this on a research grade, so purely experimental hip exoskeleton that we made in the lab, weighs 4.5 kilos, so not anywhere close to as good as the field standard. That's not necessarily what we're going for. So it's a relatively heavier device, peak torque of 15 Newton meters, so it could provide up to 20% the biological assistance. So it's basically giving you around 20% of your walking assistance at any given time with these specifications. Okay, and this is kind of the key, is how we train this. So we collected lots of data, in this case 34 subjects worth of data across lots of different activities. So we did multi-speed walking, we did standing to walking transitions, we did inclines and declines at lots of different different grades, and we did lots of different stairs and stair transitions at different stair heights. So we collect all this data, we collect the exoskeleton data, and very importantly, we collect time-synced biomechanics data. So this is all done in a motion capture lab. So there's motion capture and force plates. These are force plates that he's standing on. That measures the 6 off-ground reaction forces. We then run inverse dynamics to be able to calculate the ground truth internal human hip joint moments. So we collect all of this data. It's millions of points of data to train these big neural network models. Okay, and then at that point, once we've trained a model, we can then deploy it in real time on human users. This is kind of what it looks like. The gray is the actual human joint moment. The blue is then a scaled, delayed, and filtered output of the model. And I'll show this working in just a second. All of these data sets have been open source. So this was published earlier in 2024 in Science Robotics, and we released these huge models so other people can refine and use them as well. Okay, and this just gives you an idea of scale. So we have, again, millions of training labels in this model, in single-digit millions. We would love to see this become tens to hundreds of millions of data points, but you could see kind of a standard logarithmic curve in terms of decreasing error, in this case, RMSE error, so tracking error between what our model estimates and what the human is doing. And so this represents a lot of data, almost a year of collections to gather this kind of data. And now let's show some performance in real time. So this is someone walking around in the exoskeleton who, and all of these models are trained on what we call a user-independent basis. So that means all of these tests are done on novel users who, of course, did not go in the training data set. And we're trying to estimate their personalized biomechanics. So the blue is what the AI system is doing in real time. So that's what it's outputting and commanding to the motors on the exoskeleton. The blue is the ground truth. So whenever he steps on a force plate, so you can see wherever there's a force plate in the lab, we can calculate the ground truth. And so what we're trying to do is, of course, match ground truth to what the AI system is doing to the maximum extent possible, right? And so all of these models are tuned to try to estimate that as well as we can. And this kind of gives it some general performance. And the blue bars are our PCN or our AI system, how well we're estimating it. The brown is an interesting baseline. The baseline that we use to compare to is essentially the very best that our old systems could have ever achieved. What are all old systems? They are a perfect state estimator. So if I were to be able to estimate the modes and the gate phases perfectly, so if I had a perfect mode estimator and I just had a lookup table of biomechanics, which is how many of the controllers are designed today, that would be my performance. So that represents the very best performance we ever could have done. The fact that we can beat that with the blue means that we actually have some level of personalization going on. So that means the AI system not only knows kind of what are the joint torques as I change the different modes, but what are the joint torques specific to this human, right? So it's basically beating, if I just took an average set of joint torques from a database versus this person's very specific set of joint torques, can I estimate them better? And the answer was pretty cleanly yes. Across tasks, we can, which was very exciting to see how well the AI is not only being able to be somewhat task agnostic across these different locomotion tasks, but also personalize its assistance to a specific user across, not just, so these are level ground walking, ramps, stairs, and these are stands and walk to stand transitions. And this just gives you an idea of some tracking. You already saw it in the video, but you can see we generally have pretty good tracking as people are walking or even transitioning between tasks, between what the AI system is doing and what the human internal biomechanics are, which this is really important for getting very paired, feeling like the exo is assisting you and being a part of your movement patterns. In terms of, okay, so those are all engineering things. In terms of actual real benefits, how are we doing? And I think the answer is generally very well. We did tests, metabolic tests. So these are energy tests. So basically you put on a breath mask, measure oxygen consumption, carbon dioxide output, and look at basically does the exoskeleton reduce your energetic cost as you're walking around and doing these different tasks. We compare it to the device turned off, basically or not turned off in a zero impedance mode. So it's basically just compensating for its own internal friction versus not wearing any device versus the best controller previously determined in this field, which was the orange. And then the blue is what we call our unified controller, our AI controller. Again, it's here. Generally, the best metabolics were with the AI system. We were equal to the best in the field for level walking. We exceeded it in ramp ascent, so that was very exciting. and we are getting nice, pretty substantial benefits relative to the device turned off or to the no exoskeleton condition. And of course, you can see there is a penalty, of course, with putting the device on, but we're almost doubling, not only accounting for that penalty, but doubling the benefit from there. So that's really great. That's showing that the device is, assisting above and beyond able-bodied walking in these tests. Okay, so this is kind of our first real major demonstration of this. And what's very cool is it's the same controller, for example, for going up level walking or inclines. There's no change. There's no change in tuning. There's no change in the controller, right? It's all just using this AI system, and it's able to automatically adapt the torque profiles to best suit these tasks based on large amounts of human dynamics data in its training set. Okay, so we wanted to move on from here to kind of our next challenge. So what we just demonstrated was this AI capability for walking ramps, stairs, standing to walking type transitions, but we really want to go a lot beyond that. So that's a part of community ambulation, but doesn't encompass the wide range of different things that people do. Real human data is very messy and non-cyclic. People are very unpredictable. This is an awesome study some years ago that showed the average human walking bout. In fact, 40% of all walking bouts are less than 12 steps. So most of the time when people are walking around, they're not performing hundreds of steps of walking. They're usually doing these very small bouts of locomotion, and they transition between tasks very quickly and frequently in real life scenarios. And so how do we handle this? So right now, biomechanics data sets, or at least historically, were very limited in terms of task diversity. Most of the focus was on walking, and most of the data available that you could train an AI system is simply level ground walking on a treadmill. Over time, this is slightly expanded. So we've seen, additions of running or inclines and stairs have been a big focus. And on one of our data set, we included turns. But still, these are relatively tightly focused on a few very specific locomotion tasks. We recently released a data set that includes vastly increased a number of tasks. So we tried to collect around 100 different unique task conditions from 29 different core tasks in order to create a high diversity set of data to train AI systems. So let me show you that real quick. So the idea is we want to be able to train AI systems on enough task diversity that eventually it could generalize to brand new or novel tasks. So this is the idea of a truly task agnostic model would not only be able to perform well across all the tasks that it's seen in its training database, but actually generalize to unseen things. So that's our main goal. Towards this goal, we've collected these very large data sets now. So this is a great example. This is an open source data set that we released just barely over a year ago, and involves 29 core different tasks, basically everything that we kind of could imagine that people normally do. These include both the cyclic things that people normally study and non-cyclic tasks like going up a curb or cutting or jumping or lifting a weight or doing a lunge or doing a squat, or as many things as we could basically think of, we tried to add to this with the idea of being able to train very large biomechanics AI models with this data. Okay, so this is data that we made available. And then what was very interesting is as it turns out, if we look kind of at joint contributions, a lot of the literature is focused on either the hip or the ankle, because in cyclic tasks, these kind of dominate. In non-cyclic tasks, you see that the knee really starts to dominate and is used a lot more and in terms of the joint work. So basically larger on this means more use. And so hip and knee kind of in this data set dominated in terms of how important they were. And so this kind of goes to our tech development. The next exo that I'll present is this hip knee system that was originally created by Google X. Now it's been licensed to Skip, and we continue to work with the technology as part of a partnership. But this is a very cool, now clothing integrated exoskeleton, where basically it's a wearable set of pants where there's no orthotic cuts. So rather than kind of these big strap-on systems that we've seen in the past, the idea is to replace that with smart clothing, where part of the clothing is what we would call a zero stretch weave that allows for force transmission and the exoskeleton to apply forces to the limb, while the rest of it is more stretchy and quite comfortable. So this makes for a lot, more integrated, with the idea that hopefully in the future, people are just putting on a pair of pants and that will power them to do what they need during their day if they need help. And then this we designed to be what we would call task agnostic. So we optimize the model for task generalization, which basically means that we collected lots of different tasks and then optimize it to generalize on withholding tasks. This allows the neural network to be primarily focused in terms of the loss on tasks that it's never seen in its database, and that allows these models to then be performed quite well on a task agnostic basis. And then we extended this to a full HIPNE system, and I'll demonstrate some quick results here. So again, these are videos where in the video, the black line shows what the AI system is doing. And then whenever she's on a force plate, you can see what the ground truth is, which is the red. And of course, we want a tight coupling between black and red. And what you'll see is lots of different types of tasks, both cyclic and non-cyclic types of tasks, and even stepping over a single object, things of this nature. And again, we compare ourselves to kind of the best in the field, which are these lookup tables of normative joint biomechanics. And in non-cyclic tasks, we do it compared to impedance, a lookup table of optimal impedance parameters that have been fit to the data. And what we show here, this time we're going to use R-squared, because if I just showed RMSE, that varies very heavily on a per task basis. So a lot of people are probably familiar with R-squared. That's sort of the fit between your one line to another. So that tells you whether the shape of these are the same. And what we can see is that the AI system is getting an R-squared of about 0.8, which means there is a very tight coupling overall. That's a very high level of correlation between ground truth and our real-time estimates of the exoskeleton. This does a lot better than lookup tables, which tend to have R-squareds in the best case around 0.6. And then for other tasks, like these unstructured tasks, you can't even come up with a lookup table that is meaningful. And the performance is going to be a lot worse. But we see that our performance is maintained across both cyclic and these non-cyclic kinds of tasks, which is really a testament to what these AI systems can do once properly trained with really large-scale sets of data. And then lastly, how does it perform? And so this is some of our initial data, which was published late last year in Nature, where we tested human performance across 10 different tasks. In this case, 4 different cyclic tasks that you can see on the top, and 6 different non-cyclic tasks that you see on the bottom. And so in the cyclic tasks, we measured metabolics. So again, this whole body energy cost, we see significant benefits relative to the exo just in the zero impedance mode. That's the gray bars across all of the different tasks. Even though this exo was a very early version, it weighs 7 kilos, which is a lot. And so there's a huge metabolic penalty associated just with putting it on for carrying all that extra weight. Hopefully over time, we will all get that weight down by a lot. It doesn't need to be that heavy, but it does add a big penalty. But we're still seeing that the exo is not only making up for that penalty across tasks, but still providing additional benefit. And in our most recent tests, which were just focused on lifting weight and inclined walk, we saw about 14% metabolic benefits relative to the no exo condition, which is very exciting. We saw about 7% benefits in this a bit older version of the exo in study. And so that's really fantastic on cyclic tasks. But then extending this to non-cyclic tasks, things like sit to stand or going up a stair step. In this case, we have just a small staircase of 6 stairs, so we can't really do metabolics where they can continually do it. So or doing a lunge or a squat or lift in place weight, you'll see in general, we're seeing very substantial benefits relative to no exo across almost all of these different tasks, or at least breaking even to the no exo condition. So what does that mean? It means it's always helping you. So whenever you turn on the AI system or the assistant, regardless of what you're doing, it's going to provide some benefit. Whether it's better than no exo, that's not always, certainly with our 7 kilogram exo, it's not always just uniformly better than not wearing an exo at all, but it's generally giving very helpful assistance, and it's at least breaking even with the no exo condition. So it's at least as good or better than not wearing a device across a huge range of task variability. And as we refine these systems, this represents really just what I would say is the floor of performance gain. We can probably do a lot better than this, and we already have achieved in certain areas with various kinds of fine tuning, better performance, and I think that's going to only improve as we improve both our models and our controller capabilities with these end-to-end models. Okay, so that's kind of the end of my talk. This shows sort of the main contributions is really ability to personalize to novel users on the fly without any user-specific data, the ability to generalize to withheld tasks with AI, and removing the need for knowing everything a person's trying to do from an external. So we don't, from an external perspective, like we don't need to necessarily know the mode or the speed. We just need to know kind of their internal dynamics. And there's no tuning or heuristics, which is really a key thing that we want to get away from in this field, in my opinion, which really limits translatability of the work. And then I have 3. I'm not going to spend any time on it, but just what are we doing with this? So, I kind of showed the basic technology and proofs that it works, but what are the applications? One is imbalance augmentation. This is a big area that we're moving in, where we're using these AI systems to stabilize or self-correct balance. You can see that on kind of our perturbation platforms or simulators in the lab. This has been a big area for deployment of these AI systems. Another is in stroke. So this is, we've collected now massive amounts of data in specific to stroke, and we're using it for empowering and enabling mobility in the stroke population. This is one of our big areas. And in robotic prostheses, so extending AI systems for full leg support and replacement, and providing far more capability for these robotic prosthesis systems. So this just gives you a taste of kind of what are some of the applications, where are we going, with this kind of technology. And with that, I'd like to thank the AI for Good organization for having me, as well as the many sponsors, especially NIH and NSF, for really, doing the bulk of the funding of this work, and then all the students who have been able to participate as part of those projects to develop these very cool combinations of wearable robots, AI, and biomechanics technologies. Thank you for having me.
Well, thank you so much, Aaron. It was a great, insightful presentation. So we would like to hear from the audience. So if you have any questions, please type them into the AI for Good neural network. We have received a few, and so the first one is, how do you balance personalized biomechanical assistance with user autonomy when the AI decisions might conflict with the user's preferences?
Yeah, it's a great question. In many ways, that's why we are trying to go to this kind of model that, I think that question or that problem arose far more when we were doing the external state, what I would call is the external state estimation. When an AI model is, let's put it this way, when an AI model is trained well and is working well, that is fully based on the internal state, what is very interesting and probably is non-intuitive to people who have not worn these, is that perhaps the best AI models you barely notice at all. As in, it's so well synced that you no longer can tell that it's really assisting you. So your body is doing the high-level commands, but it is in sync with you, where you can no longer tell that the device is on until we turn it off. And then the minute you turn it off, it's like, oh, whoa, now, it feels like you just added extra gravity on someone, right? So, and that is what we see. So, and where we are trying to get to is that the AI models should be in such sync with your body that you probably cannot fit. You are so adapted to it that you cannot notice that it's doing anything. And to us, that's the best experience, is that it just feels like, I can do everything that I want to do, and I'm really not noticing the robot at all. If you're noticing the robot or feeling it heavily, that's usually not a good thing, which sounds odd. When you first put it on, of course you're going to feel it, and it feels a little different and everything. But once you get in sync with these systems, the goal is that it is perfectly synced, or as well as we can, to your internal biomechanics. So basically, as you do a different task, it's just providing a proportion of the energy required to do that task, and is relatively unseen otherwise, or and unfelt. And a lot of times people, after adapting for a while, are like, is this device even on, right? And you can't tell unless you turn it off, and then suddenly everything is much harder to do, which means that's a very successful integration. And that is what we're trying to go for in the AI, where there is no difference between what the human is wanting to do and how the AI is assisting them.
Okay, no, that's excellent. And we have a follow-up question about how what are the biggest challenges when it comes to scaling this technology for widespread adoption, like cost, accessibility, and adapting to diverse user needs?
Sure. I mean, obviously the answer is, in some ways, there's a lot of barriers, which is part of why this technology isn't out there. I focus just the talk on the control, because I do think that's where AI in particular has its has the biggest potential benefit. It's actually not the only area where AI can be beneficial for this kind of technology, but it's kind of, in some ways, it's the biggest one where AI can play the role. But in terms of wearable robotic technology as a wider piece, not just the AI piece, there are lots of additional challenges, certainly cost. And with all robots, it's not just the cost of the robot, but the maintenance of the robot and the repairing and being able to maintain the robot for long periods of time, especially out in real environments. That is always been in any robotic application, that is challenging. And so I don't think there are many challenges in the robotics field that extend beyond the wearable robot field that are not unique to wearable robots, that need to be overcome. Certainly cost scaling is a big issue. So is the ability to maintain and keep these robots working over long periods of time. That's quite challenging. The hardware side, though, is specific. I didn't talk a lot about hardware. I still think we have a ways to go to making interfaces that are seamless, that are super comfortable. I talked a little bit about like moving towards pants integration. I think the idea of, rather than, I think the traditional idea of these wearable robots are these big strap-on suit-based exoskeleton systems. I hope we're sort of moving beyond that, right? Like those are cumbersome, they're bulky, they have giant metabolic penalties, right? You're never going to see a metabolic benefit with a system like that, because the penalty is tremendous. Instead, I really like, and some of the companies are working more towards this idea of, it's robotic clothing, right? It's not an exoskeleton, it's not these big strap-on things. It's a boot or a shoe or a pair of pants, or a vest that I'm putting on, and that is very transparent, very comfortable. Ideally as comfortable as clothing, and it's easy in theory, and it's easy to don and doff as clothing. We are not there yet, especially on the don doff part. Usually it takes significantly longer, and sometimes it even takes another person to help don doff, right? We need to be able to, somebody needs to be able to put it on themselves, even if they have some levels of impairment, and do so timely and quickly, right? Like I think there are many challenges still on the hardware. I like the direction that the field and some companies have moved, but we still don't have devices, I think, that are on the market that are just plug and play in terms of from the hardware's perspective, where I can just put on a pair of pants and run, right? Like we're not there yet, but it's moving in that direction, better textile integration and things of that nature.
Yeah, so we have a few more questions. Like really, I think our audience is very much interested in this topic. So what are you also currently researching AI-powered wearable robots specifically for individuals with complete paralysis, like fully locked?
Good question. Okay. The answer is no. That is not a major focus of my lab group, but there are other lab groups, both at Georgia Tech and elsewhere, that are absolutely doing that. So you know, I would almost talk about that in a very different way. So there are exoskeletons. One of the leaders in the field is a company called Wondercraft, which is based in Paris that we know well. The people at Georgia Tech work with them. But that's one example of one of the best examples of what we would call these self-balancing robotic exoskeleton systems. So in the case of complete paralysis, the techniques that we are researching and using will not work because basically all of the systems that I show that my group focuses on is for what we would call partial assistance, where the human is doing some and the robot is doing some, and there's shared autonomy between the human and the robot, right? So that all of our research focuses on this human-robot collaboration. In the case of complete paralysis, you cannot do that. The human won't be able to generate basically any joint torques whatsoever, and so the robot so it becomes a robot that has to do everything with a human rider, essentially, that is just on for the ride and has, you know, other than maybe a little bit of trunk control in some cases and arm control, has very little capability, at least to do any of the locomotion capability. And so at this point, the robotic control problem begins to look a lot more like traditional biped robots rather than, you know, wearable exoskeleton robots in terms of both the control, how everything is formulated. Absolutely, AI can be utilized in this. Both, you know, traditional kind of AI systems that do state estimation. So, you know, before we did internal state estimation, we always used AI to do external state estimation, like estimating, look, there's a stair in front of you. You know, maybe you have a vision sensor and it tells you, okay, you need to go into stair mode, or, you know, they're trying to sit down, right? Like, so these types of things, either based on the trunk or based on some joystick hand controls, can be used to help control the device and provide, you know, that sort of capability. So the answer is absolutely yes. The exos look very different. The controls problem looks different. But AI is certainly being utilized in that very different field to help that subset of population that cannot provide, you know, basically have any sort of autonomy or shared control.
Well, that's great. We had Wondercraft last year at our global summit in Geneva, and it was like really incredible. There was a French tennis player who was able to stand fully upright, I think for the first time in like 15 years on stage. So that's, yeah, like this like really,
it's very cool. Yeah,
really amazing. So we have another question so we have Lendert who is wondering, your model is trained on data of healthy subjects. How does that translate to movement for impaired users? For example, stroke or amputees, especially in transfemoral amputees in cases where the knee joint is significantly lower than in a healthy subject.
Okay, yeah, so let me start by just answering the question more generically. It's a great question, and this is sort of, you know, much closer to where the research is at in some ways. So yes, all the proof of concepts, you know, the AI systems that I showed in this, which is more, you know, I would kind of consider it more technology development, was all done with able-bodied users. In any sort of clinical trial scenario, we have to start and demonstrate an able-bodied, I'm just kind of stating this before we can go to clinical populations. So that's why, a large amount of the work is done in able-bodied populations, and only things that are very successful then move on to actual clinical trials. In terms of the models, I would say that it's an open question whether the able-bodied information is valuable or not to clinical populations. Our baseline assumptions were that it was not, in that in clinical populations, the movement patterns are very different. The impairments are very different, and the way in which the biomechanics are generated are substantially different from whatever angle you want to look at. And so we thought, well, then the mapping from the device to the internal dynamics of the human are just going to look so different that the able-bodied data might be unhelpful. That was our assumption. Turns out that assumption may not be correct, but the assumption was if I have a new population, I need to recollect massive amounts of data from that population, from their specific types of movement dynamics. And in stroke, it's very heterogeneous. So that means every individual walks quite differently. And so the assumption was we need a lot of data from lots of different individuals. And it turns out that mixing those models with able-bodied data is beneficial for predicting personalized biomechanics on a novel stroke individual. So we actually do a mixture of data across different populations because it turns out that is good for AI. But the assumption was that we didn't, that wouldn't work. And certainly training with data from a specific patient population does improve our capability on that patient population. And so part of our objectives have been, if we want to translate to a specific population, for us, our focus has been on stroke and able-bodied or mobility impaired to some degree, older adults. We need to collect giant data sets on those. And so we are trying to create those, curate those, and release them so that we can have patient-specific AI models. And that is very valuable. But the able-bodied data, it turns out, is actually quite valuable to include in combination, just because probably it fills out that task space and just gives a lot more data for training the convolutional layers, or basically the feature capturing of the signals likely gets a lot more robust.
No, that's amazing. So we are moving towards the end of the session, but I wanted to ask you one last question. So if we look 10 years into the future, do you envision a world where wearable robotics are common as, let's say, like smartphones? What key breakthroughs are needed for that to be?
So this is kind of funny because this same question was asked to my former postdoc advisor is Dr. Dan Ferris, who's a very well-known exoskeleton researcher, and he predicted in 2010, based on the breakthroughs that we had, that in 10 years, people would be wearing these throughout the world. I think time and time again, people think that the technology, I think in 2016, there was this huge, with WearCon and these other conferences, there was a huge resurgence of, oh man, this technology, it's working. We've broken the metabolic cost barrier. We have, really, technology that's benefiting people. We'll be able to deploy this in the next year or two. There's always been challenge after challenge in real world deployment that makes this take longer than we think it will, which is unfortunate. So, I would be careful about the 10-year, it will be everywhere, but I would at least hope that we'll see it deployed in specific arenas, because I think what we have demonstrated is that for very specific tasks, like if I just need to do, lifting or walking or other things, that we can deploy these systems. I do think we'll see more and more. There are a lot of startups in this space. There are a lot of really good companies and now highly trained people who have seen it for a number of years that are trying to deploy the technology. So I'm relatively optimistic that we're going to see more of it get on the commercial market and be made available. I still think there's a lot of work between where we're at now and having, these, what we're really kind of moving towards is this idea of these foundational models or what we would call task agnostic models that are able to be basically helpful to you on everything that you want to do. I think it does feel like we're getting there, but there's certainly major barriers still to, before that's going to be commercially out there and viable to people. So will it happen in 10 years? I don't know, but I think the field has really began, especially with the advent of deep learning and these big AI models. The controls problems are feeling much more solvable than they were 10 years ago. And so I do think, at least in terms of that barrier, it could be cleared. Now, other things, regulatory of AI in clinical populations and costs and manufacturability of systems, that's all things that I can't control and are things that companies are going to have to deal with, and are still barriers that will have to be crossed before we're seeing more wide scale deployment in communities and homes.
No, thank you so much, Aaron, truly for sharing your insights, as well to all the attendees for making it such an interesting session. So we are very much looking forward to continuing the conversation in our upcoming AI and Robotics Discovery series, and as well at the upcoming AI for Global Summit in Geneva. Mobility, rehabilitation technologies, prosthetics is going to be a big piece of our program on main stage and the other stages as well. So now I think it's the end of this AI for Good event. So thanks, Aaron, again, and I will give back the floor to Anna for the closing information. Thank you very much.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.